We talked in the last video about having a cup and setting it out and letting the water evaporate. Let's say, instead of just letting the water in the cup evaporate, what if we put that water into a flask and stoppered it? So we put a stopper in the top of the flask so that the water, as it evaporated, could not escape. It couldn't go out into the atmosphere. It was trapped inside that container. What would happen is, over time, you'd start off with very, very little water up here. As the water starts to evaporate, you'd get the water molecules bouncing around in here, and eventually some of those water molecules would actually bounce back into the surface of the liquid. Some of them would have enough energy they could just bounce off of it, keep staying in the gas phase. But many of the water molecules that hit the surface, and actually I would say most of the water molecules that hit the surface, actually get recaptured. And so at first, there's more water molecules that are escaping the surface than are being recaptured. But eventually, there will be developed a certain concentration of water inside the container in the gas phase that is in what we call a dynamic equilibrium with the liquid water, where you have exactly the same number of water molecules escaping and going into the gas phase as there are water molecules being recaptured into the liquid phase. And this will always happen. You might have, a split second here and there where, you get a few extra percent escaping than being recaptured, but it all evens out. It's required to do that, because if you have an extended period of time where you have more stuff escaping into the gas phase, well, you're going to get this glut of water in the gas phase that, just statistically speaking, must start to get recaptured. Just very laws of the universe, statistically speaking, you can't have a non-equilibrium inside this system here. Now we can manipulate that equilibrium a little bit, though. We can mess with it. So just because you will always end up with an equilibrium doesn't mean that you can't do things to play around with it. So if you have a system like this one here that's at a dynamic equilibrium, you have the same number of molecules evaporating as are being recaptured. If you then take this movable piston and pull it up so that there's now more volume for the gas to move around in, well, now the gas isn't going to be recaptured as often because it has more space. There's actually physically longer distance that the molecules have to travel before they hit the walls of the container, and thereby have a chance of going back into the being bounced back into the liquid surface. There's actually physically more volume for them to move around in, so they are recaptured less. And so for a little while, you actually will have not have an equilibrium. You will have more being more going into the gas phase than you have being recaptured. But again, eventually it will get back to the exact same equilibrium we had here. Same thing here if we compress the gas. Give it less space to move around in, well, now more of it will be recaptured per second than is being put into the gas phase. But again, eventually you will get back to that dynamic equilibrium. So if we do something here, so let's say we had some kind of an equilibrium before, and we mess with it, we do something to it, eventually, after altering our system here, it will get back to the exact same dynamic equilibrium that we had initially. That will always happen, but we can mess with it a little bit, and it will change the system for a little while until it eventually regains its dynamic equilibrium. So this leads us to a question here. What happens to the vapor pressure of a substance when its surface area is increased at constant temperature? And I'm going to add one extra thing here. This is covered, I guess you can say. Like the gas that's in our system here can't escape. It's not open to the atmosphere. So if it's not open to the atmosphere, we increase the surface area of the liquid and we keep it at a constant temperature. Will the vapor pressure increase? Will it stay the same? Or will it decrease? So I want you to pause the video here for a second and think about this. And by the way, if I haven't made it clear up to this point, the vapor pressure here, this is just a measure of how much of the molecule is in the gas phase. Vapor pressure is just kind of a fancy way of saying how much gas is present. So will you have more stuff go into the gas phase, the amount stay the same, the amount of molecules in the gas phase stay the same, or will you have a decrease in the amount of gas present? So go ahead and pause it and think it over for just a second. Okay, hopefully you thought about that and you came up with an answer. I would bet that you either thought this, that the vapor pressure increases, or maybe this one. I don't think there's anything that's described here that could make you think that the vapor pressure is decreasing. Well, actually, I take that back. There is a way that you could think that. But in my experience from teaching this lots of times, the majority of people go with A, that the vapor pressure increases. So if that was your answer, congratulations, you are in the majority, if that's something you're excited about. But it's not the correct answer. B is actually the correct answer. And if you're thinking, well, hold on a second, you said that when the surface area increases, that means there's more space over which the liquid molecules are able to escape, so therefore you should have more stuff going into the gas phase, so therefore you should have a higher vapor pressure. And to that I would say you are correct on all counts. Everything that I said there is true. But it's not complete. You're missing a part there. And the part you're missing is, you might have guessed, is part of it is from what I added in there. I told you that the gas can't escape. So it's not open to the atmosphere. It is in a closed container. Any gas that leaves the liquid phase is trapped inside there, which means that when you increase the surface area, not only did you increase the area for the liquid to escape into the gas phase, you also increase the area for the gas to be recaptured. So it works both ways. It's not only easier for stuff to evaporate, it's also easier for things to be recaptured. And so the vapor pressure actually stays the same, assuming that you were at an equilibrium before. Changing the surface area is not actually going to have an effect on that. So now that one was a little bit tricky, but hopefully, in my experience, the questions that are a little bit tricky that make you think also help you learn things a little bit better. So hopefully that helps you with that. Just a quick note here, again on vapor pressure and how it changes with temperature. As you could probably guess, as you heat up a liquid, its vapor pressure is going to increase. So again, the vapor pressure is just a measure of how much of that liquid has escaped into the gas phase. How much of that molecule where the majority of it is there in the liquid phase, but some of it has escaped. What is that pressure of the gas above the liquid? And so as you heat it up, that vapor pressure increases. And it will increase up until, well, it'll still increase past this, but normally we kind of stop considering the vapor pressure when we get to the boiling point here. And the boiling point of anything is just defined as the temperature where the vapor pressure is equal to that of the atmospheric pressure, the pressure that is on the liquid itself. So when you boil water on your stovetop, what you're doing there is you're heating it up to the point where the gas molecules that are escaping from the liquid phase and going into the gas phase are actually at the same pressure as the atmosphere that we experience all the time. They're at 1 atmosphere of pressure, or 760 torr, or millimeters of mercury. And that is the definition of the boiling point. And one of the more interesting things you can do, and I wish I had a video of it here, but I don't have one handy, but you can look up videos on YouTube of people boiling water at room temperature. And it's actually not all that difficult to do if you have the right equipment. If you have a good pump, a good air pump that sucks air, not compresses it. So not an air compressor, but an air pump. You can suck the air out of a container that has water in it, and you can boil water at room temperature. Again, fairly easily, because when you suck all the air out of the container, the quote atmospheric pressure inside that container is no longer 1 atmosphere. It is significantly lower. And so as soon as the vapor pressure of the water that you have in the container matches the pressure of the, again, quote atmosphere, again, it's not actually the atmosphere, but the atmosphere inside the container, as soon as they meet, presto, you have boiling water at room temperature. It's a pretty cool thing to see, actually. All right, I think we'll call it there for this video. In the next one, we will start talking about these regions here, where we are putting energy into our system, but not getting any temperature change as a result, which means that we're going through a phase change. And more specifically, we'll talk about the Clausius-Clapeyron equation. So I'll see you in the next video.